this is 9-5, day 1. Learning target is about applications, but they really tend to focus on looking at navigation and surveying. Today, we're kind of focusing on the basics of how trigonometry can relate to navigation. Okay, and in particular, that's kind of referring to some techniques that are used in sailing, sea travel, air travel, the type of navigation where you're left to kind of find your way without man-made landmarks to guide where you're going, kind of like a plane, all right? That type of thing. We're going to look at kind of the basics and how to set up a good diagram, and then I'm going to show you one example of the kind of problems that we'll work on solving. Okay? Everything in navigation is relative to due north. Okay? From there, we open up clockwise, and we give an angle measurement that refers to your direction. Okay? For example, if we were to look at due east, okay, relative to this line pointing north, due east makes a 90-degree angle if we open up clockwise, which is why east is 90 degrees or 090. Okay, we always use a 3-digit number for our course. Okay, that's what we're referring to right here. Due east has a course of 090 or 90 degrees. Okay, that would mean anything between 0 and 90 would refer to the direction of northeast. South is 180. West is 270. Those are kind of reference points. So when we have an angle or a course, you know the general direction in terms of northeast, southeast, southwest, or northwest. Okay? Let's look at this example down here with the ship. All right? What would we estimate his course is? Okay? Take a second and see if you can put on a little estimate as to what that boat's course is. I'm going to say 120 degrees, okay? And that's consistent up here with the fact that that's between 90 and 180, which means the ship is going in the relative direction of southeast, which it looks to be, okay? I'm going to enlarge this diagram and kind of put it over here. So these bearings are 120 degrees. I'm using, if you see that in the book, I'm using that term because the book does as well. Bearings and course are referring to the exact same thing. Those two terms can be used interchangeably. At both points we have a line referring to north, and those two lines are parallel. Okay? So this angle right over here is 60 degrees. If we wanted to generalize that, if that angle is theta, this angle down here is 180 minus theta. Okay, notice how they're both kind of on the inside of that reference to north. Okay, that comes up quite a bit. So those are really the basics about bearings and setting up a diagram. Let's take a peek at an example. A ship proceeds on a course of, let's make special note right here, of 300 degrees for 2 hours at a speed of 15 knots. 1 knot is 1 nautical mile. It's slightly different. Instead of 5,280 feet, a nautical mile is 6,080. I think it's either 6,080 or 6,008, one of the two. It's pretty close to a regular mile. Then the ship changes course to 230 degrees. Continuing for 15 knots for 3 more hours. How far is the ship from its starting point? Every diagram should start with the same thing. Referencing that starting point and then drawing a line due north. Okay? It tells us its original course is 300 degrees. Think general direction. Okay, that's between 270 and 360, which means the ship is going northwest. Now, my diagram doesn't have to be perfect. Okay, it should just kind of point in the general direction of something like that. Okay, as soon as I get to that new point, I am going to draw another line due north. Okay, every time you reach a new location, it's important to have that line on there because the second location right here, this is where the ship is going to change course. And anytime I change course and I'm going in a new direction, I always start relative to due north. So let's throw some information on here. This angle is 300 degrees. That means in here, that angle is 60, because those two have to add up to 360. And this leads us to that last fact we talked about in the previous slide, that this angle right here is 120. Okay? Because that angle and the 60-degree angle must add up to 180. Okay? Now, as far as the distance goes, we'll just leave it in the unit of knots. 15 nautical miles. Whoops. Hold up. That was its speed. It went at that speed for 2 hours. This should be marked on here that it went a distance of 30 knots. Okay? 230, again, think in terms of general direction. That's between 180 and 270. So instead of continuing its course northwest, the ship changes and starts to go southwest. Okay? I'm already going to put on here that the distance is 45 knots because it continued at the same speed for 3 hours. Now what we're looking for is this distance right here, a straight line distance from its original starting point to where it ended. Okay, hopefully you can see that we have a triangle that is set up as a result. Okay? A couple other things I have to put on here. That change in direction of 230. Okay, remember that starts relative to north and I go clockwise. That is that whole thing. Okay, that's 230. This is why the 120-degree angle was important, because now I can take that out, and this angle that's inside the triangle is 110. Okay? That's really all the information I have. I suppose I could add that this angle right here is 130. I'm not suspecting I'm going to use that, but, well, I guess I know what it is. Good for me. Good for us, I guess. But that's really all the information we have. And once you have that diagram set up, you look at your information and say, okay, what's going to work here? We've got a lot of tools that we've developed over the course of the unit. It's just a matter of picking the right one. Okay? I don't have any evidence at all that this is a right angle. Well, in fact, I have evidence specifically that this is not. This triangle has a 110-degree angle, okay, which means these other two can't be 90. So it's not a right angle. That means SOHCAHTOA cannot be used. Okay, all the stuff that we did in Learning Target 1, we can't use. That leaves the law of sines and the law of cosines. And what I notice here is I have side, angle, side. Okay, now this may take some practice and some getting used to, but if you'll remember from 9-4, this is the case where we use the law of cosines. Okay, the one case where we're looking for a missing side, and the law of cosines is the exact tool that we want to use. X squared, just to get this set up, is 45 squared plus 30 squared minus 2 times 45 times 30. I am hopelessly running out of room. I'm trying to squeeze in the cosine of 110. I'm going to try that again. Times 45 times 30 times the cosine of 110. Okay, this is the step that we referred to previously where it's beneficial to just take that whole expression on the right, just throw it in your calculator. You're going to work with some really big numbers. There's no use trying to simplify it by hand. We're just asking for a mistake, even though it would be good practice for order of operations. It's just not the right time to do so. And we get a large number, 3,848.5. Final step will be to take the square root. And we get 62, which means x is a distance of 62 nautical miles. Okay? Again, the point I'm really trying to make here is once you get your diagram set up, which can be a little bit of work, and the diagrams can be a bit confusing at times, that's where you really have to focus and do your work. Once you get it set up, it's like all these other problems that we've practiced solving. It's law of sines or it's law of cosines. And again, typically, if you didn't recognize that this was a case for a law of cosines, the worst that could happen is you would try the law of sines. You would see that it doesn't work because we don't know a pair, opposite side and opposite angle. We don't have a pair of those two things in this triangle. Okay? Which means the only alternative would be the law of cosines. We'll call it quits there. We do have more to look at in 9.5 Day 2, but this is a good start on navigation, and we'll look a little bit more at the topic of surveying in Day 2.